Hello, everybody. Welcome back to another discussion in dynamics. This one will be a little bit spooky because it's Halloween. Happy Halloween, by the way, everybody. And plan for today is following. We are still in the momentum chapter. And today we'll just learn about direct impact, coefficient of restitution, and two examples. We're going to do two examples. Yeah, I have nothing else to say. So let's do a brief lecture review. So I just would like to provide you a definition of coefficient of restitution, at least seen through my eyes, okay? So this is a brief lecture review. And we will cover coefficient of restitution. So I would like you guys to imagine that situation. Pre-impact and post-impact. So let's say that we have two particles, okay? Small particle and big particle, okay? And this guy has velocity a pre-impact, and this guy has to have smaller velocity, right? Because the little guy has to be able to chase the big guy, otherwise we won't have an impact, yes? So this will be VB pre. And of course, VA pre must be larger than VB pre, yeah. Just as a side note. Okay, and post-impact, wait a second, because I believe that I use different nomenclature than was used in the lecture, yes? Professor Sony, I think he uses like VA minus here and VB minus, yes? And then in here he will be using like VA plus and VB plus. I don't personally like it. And by the way, every single instructor in this course uses this nomenclature. For me, it's too many minuses, too many pluses, okay? And I keep forgetting what minus means and what plus means. I propose this nomenclature. I propose superscript pre for pre-impact and superscript post for post-impact. In that case, I'm never lost in my solutions. Sounds good? Yeah. Okay, so post-impact, we will have, again, our two particles. But this time, this guy will be faster. It will be VB post and VA post. Yeah. So the definition of coefficient of restitution is following. Difference in velocities post-impact divided by difference in velocities pre-impact. And this is equal to VB post minus VA post divided by VA pre minus VB pre. And that's it. This is our coefficient of restitution equation. Any questions? Yeah, I have one question. So imagine that pre-impact, so this is what I want to say. This equation corresponds to the situation on the board. In other words, this equation corresponds to a situation where every single velocity points to the right. But now, we can have a situation pre-impact that these guys are coming closer to each other, yes? These velocities are going to face each other. We can have such a situation. It is possible. So what I should change in this expression so that it is true? I am going to change this sign. Do you see? Because it corresponds to VB pre. Okay? Also, so that's all I want to say. Yeah, that's it. Yeah. So anyway, also this is what I assumed. These directions are assumed by me. So I just assumed that after the impact, all of the bodies will go to the right. Yeah. However, what will happen if after the solution, at the very end, one of these dice turned out to be negative? What does that mean? That we have to flip yeah. So that means that the particle goes the other way. Okay, that's all. That's my brief lecture review. Any questions? So let's do examples maybe, okay? You know what to do. Please read and understand problem statement before we start our solution. And by the way, second round. Yeah. Okay. All right, what do we have in here? We have two particles, right? We have this particle, that big particle that is at rest, and we have little guy approaching that part, the other particle. We know coefficient of restitution between them, and we know what is the coefficient of friction between the second particle and the ground. And that coefficient of restitution will be used only in part B. So this is my solution. Let's see what happens pre-impact and also post-impact. So pre-impact, we have little guy approaching big guy, VA pre, and it has mass. And this guy has big mass, but it has no velocity. After the impact, let's assume that they all will be pointing to the right. VA post and VB post. Okay, let's write our momentum equation, because momentum is preserved during the impact, at least unconstrained impact. Yeah, in this case, momentum is preserved. So we will have, if this is correct, if this is positive direction, we'll have M VA pre, and this is equal to M VA post plus big M VB post. Okay, so how many equations do we have? One equation, and I think two unknowns, because we know everything that is happening before the impact, but we have no idea what is happening after the impact. We must figure it out. Okay, so I propose that we go for the coefficient of restitution equation. So we'll just use our definition. E is equal to difference post divided by difference pre-impact. So that will be VB post minus VA post and VA pre minus VB pre. Okay. So I think that this guy was 0.4. This is 0.4. They told us. This guy was at rest. And this one was how many? 2? This one was 2. Okay, great. So we ended up with E is equal to, or we ended up with 2E is equal to minus VA post plus, let's redraw it, rewrite it, yeah. VB post minus VA post. Okay, we found our second equation. Okay, any questions so far? Awesome. So this is our second equation. Let's put it together. Oops. Okay, so we'll have this equation, and we'll also have this equation. This one and this one. 2 equations and 2 unknowns. Yeah. However, I like when VAs are one above or below another, and VBs as well. So this variable here plus VB. Okay. Okay. 2 equations, 2 unknowns. Let's do it. Let's plug in values and let's see what will happen if we are able to find it. So if I plug in values, we'll end up with 1 is equal to 0.5 VA post plus 2 VB post, and this will be 0.8 minus VA post plus VB post. Okay, solve it, and you will end up with VA post and VB post equal to respectively minus 0.24 meters per second and 0.56 meters per second. That's it. That's the answer. Yeah. And by the way, one of them is negative. So that means that my assumption was incorrect, yes? So that means that post-impact we'll have such situation. We have little guy here, big guy here. This guy has 0.56, and this guy will have 0.24, but this direction. Questions? Yeah. And your name is Kevin. Yeah. I don't want anything from you, first of all. Yes. Listen, my answer will be following. Convince us that you know how to solve the problem. Okay. I will, just for the heck of it, I would draw this drawing. I would draw this drawing. It clearly means that you know which direction is pointing. Yeah. If I am a grader, this is enough for me. Okay. I don't like such questions, because it seems like you are like afraid of, oh my God, I'm gonna lose all of my points on the exam. Come on, man. Like, life is, you should enjoy your life, instead of that, yeah. Worrying about such things, yeah. And even if you notice that if somebody takes points for that on your exam, you can negotiate with us after, yeah. Okay, any other question? Okay, so this is not the end of the problem. This is just the end of part number 1, yes? because part number, they told us that, after the impact, the big guy is going to travel still, yes? And they told us to find how much distance it will cover. Okay, so let's do it very quickly. Part B. Part B. So we'll have work energy method this time, yes? Work energy. Wait. So let's do configuration A and configuration B. So I believe that we'll have ground in here and also here. I believe that our body starts from here with velocity 0.56, and it has big mass, and it has mu k in here. And I think it starts from here, yes? So let's mark that point, because our body at the end will be somewhere here. Yeah? And it will have a velocity final equal to 0. And I think that they ask us to find this distance. Yeah, this is what they ask us to find. Okay, so we are done with our beautiful drawings. Let's do for T1 plus V1 plus U12 non-conservative equals to T2 plus V2. And let's find these 5 guys. T1, V1, T2, V2, U12 non-conservative. Okay, I am not going to ask you for help, okay? This is too easy, okay? We have velocity at the beginning. Yes, we have. So it will be 1/2 big M 0.56 square. At the end, body stops, 0 in here. Okay, do we have springs in the system? No. Do our bodies change elevations? No. 0 here, 0 here. Okay, we have only work of friction. So we have U12 of TF. So let me draw free body diagram very quickly. So this is our mg. This is our n. And I also think that we have a friction force acting this direction, yes? And this is our trajectory with ds pointing this way. So I think I can write right now integral from 0 to d of tf ds, negative, of course. And I think that we have kinetic friction. So it would be tf is equal to mu kn. And I think that n minus mg is equal to may. However, due to our ground, this is 0. So we can clearly see that n must be equal to mg. So our tf is equal to mu k mg. This is constant. And we like to integrate constant things. I mean, we don't like integrating at all, yes? But it's easier to do it when it's constant, yes? You know what I meant. Great. So this is our work dissipated, our energy dissipated. Okay. So I think that I have enough space in here to solve that problem. So what we will have? We will have 1/2 m 0.56 squared. And this is equal to, minus mu k mg d is equal to 0. So this can cancel out, and we can end up with D equal to 0.56 squared divided by 2 mu k g. Grab your calculators and obtain that D is approximately 0.04. meters. Ta-da! The end of the problem. Any questions? Yeah, that part B was just to refresh your memory on work energy method. I don't see any questions. So, example number 2. As usually, please familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? We have a laptop that was dropped on the floor, and we're gonna model that laptop as a particle. So that particle was dropped, it rebounced, and they ask us to figure stuff out. Yes, this is basically the problem statement. And that problem consists of 3 parts, okay? So part 1, in part 1 we will just figure out the velocity the velocity that our laptop will have when it hits the ground. So it will be again work energy method. Let's draw configuration A, config B. Let's draw our ground here and here and here. So I believe that our laptop starts from here, and it has mass m and velocity initial 0. And I think that it is dropped from 1 meter, yes? I believe so. And at the end, our laptop will be here, and it will have some velocity, yeah? It will have v pre-impact, which is equal to v pre. Okay, we're done with our beautiful drawings. Now let's use work energy method to figure out what is v pre. So we will write T1, V1, and we will find these 5 guys: T1, V1, T2, V2, U12 non-conservative. Okay, our laptop starts from rest. So this is 0 here. This is 1/2 mv3 squared. There is no dissipation of energy in the system, so 0 here. And in order to find our potential energies, we will just put our datum first in here. Datum. Okay, so at the end, our elevation of our particle is aligned with the elevation with the datum. So this is 0 here, 0 in here. And at the beginning, we have mgh, which is 1. Great. Yeah. A little bit boring today, don't you think? We do that for the 7th time. Yeah, sorry, guys. Yeah, just let's do it quickly then. Okay, let's do it quickly. And for dessert, part number 3 is impact again, okay? So for dessert, we will have impact, okay? Let's do it quickly. Okay, let me plug back these guys in the original equation. So we will have mg times 1, and this is equal to 1/2 mv3 squared. M cancels out, and v pre is equal to 2g times 1, yes? grab your calculators. I did it yesterday, and I obtained that this is equal to 4.429 meters per second. Great. Part number 1 done. Just in case. Questions? Okay, I see that you are very excited. So we're gonna do part number 2 that is exactly the same as part number 1, okay? But this time we will just figure out the stuff after the impact, okay? So now part number 2. Part number 2, which is again work energy method. Okay, so again we will have our ground in here and here. And this will be configuration A, config A, config B. And this time our particle just rebounded off of the ground. Okay, so we'll have V post, and eventually our particle will stop at some elevation. And I forgot how big was this elevation. Wait a second. I'm gonna scroll up the board, okay? Okay, it's 5 centimeters, yes? The elevation final is 5 centimeters. So I'm gonna put 0.05 in here. And that's it. Okay, so again, T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And again, find these 5 guys. T1, V1, T2, V2, U12 non-conservative. So we start with some velocity. We have 1/2 mv post squared. At the end, we have no velocity, so 0 in here. No dissipation of energy. And potential energies, we just gonna put datum here. And we clearly see that potential energy at the beginning is 0, and at the end we have mg times 5 centimeters. Okay, plug everything back into our equation, and we'll end up with 1/2 mv post squared. This is equal to mg 0.05. So our v post is equal to 2g 0.05 square root, and v post is approximately 0.990 meters per second. Great. Questions? Okay. So we figure out what's happening before the impact and after the impact. Okay. As I promised, impact for dessert. Okay. So now part number 3. Let's draw our momentum diagrams. Okay. By the way, last discussion I promised you that I will bring you sneakers. Do you remember? Yeah. So anyway, I kind of brought you sneakers, but after coming back home, I realized that actually your answer was not that it didn't classify for such a price. Okay, but you must be more active, and then I will give you sneakers. Okay. Yeah, I was just too nice last time. Okay. I was really disappointed when I was coming back home. I was like, oh, I spoiled him more even. So okay. Sorry. You're welcome. Yeah. Anyway, momentum. Let's see what happens at instant 0. Instant t0 equals to 0 minus, okay? And then I also would like to see what happens when t is between t0 and t final. And also I would like to know what happens at instant t final 0 plus. Yeah, I don't know what these guys are doing here. Okay, so pre-impact, we have our ground in here, and we have our particle in here. We have exactly the same situation at time 0 minus and 0 plus. However, 0 minus means very, 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 very low number below 0. Yes, and you know that from calculus. Yes, and 0 plus means very, 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 very the number that goes that approaches 0, but from the positive side. You know that. I hope you know that. Yeah. Yes, Trevor.
So are we not using the kind of the negative value that we're getting?
We will see. We will get there. Yeah. So yeah. So t0 will be 0, and this will be 10 to minus 3. Yeah. Maybe you're right. Maybe I am wrong actually in here. So let's say that this is time. Okay, we can do what Trevor said. This is 0, and this is 10 to minus 3. Okay. My point was just to show you seconds, of course. My point was just to show you that impact is like at very, very, very small period of time. Yeah. I don't know where they get 10 to minus 3. To be honest, I have no idea. I don't know how much impacts usually take. I have no idea. Yeah. Anyway, so pre-impact, we have such situation. We have V pre, yes. And by the way, we found it. The whole point of part number 1 was to find that V pre was 4.429 meters per second. Yeah, this was whole point of part number 1. Part number 2, from part number 2, we know that this guy has velocity v post. Yes, where v post is 0.99 meters per second. Okay. And we also know that this has mass. Okay, and now our free body diagram. So we have for sure mg acting on our system, and we have also n, reaction force. So in impacts, please neglect mg. When it comes to impacts, we don't care about mg. The contribution of mg is so small that it can be negligible. Okay? That impact of reaction force, on the other hand, is significant, and that n causes all the dynamics behind that phenomena. Okay, so n causes that body to flip the velocity direction. Okay, this is all caused by n. There are no other forces acting on our system, so let's not forget about our integral from t0 to tf dt. Okay, and now momentum equations. Momentum equations. Let's do momentum equations along the y direction, with this direction being positive. So at the beginning we have v pre pointing downwards. Yes, so it will be minus m v pre. And this is, then we have impulse from t0 to t final of n dt, and this is equal to m v post. Okay. To be honest, I forgot what they were asking us for. Can I scroll up the board? Yeah. They asked us to find impulse. Okay. So they ask us to find this. But let's save some ink. I'm gonna write IMP, okay? IMP. So our IMP is equal to MV pre plus MV post. Let's plug in values. IMP is equal to 2.75, 4.429 plus 0.99. Grab your calculators and obtain that our IMP is equal to 14.902 newtons times seconds. Answer. Great. Any questions to what happened so far? Okay, this is not the end of the problem, yes, because we have still one more part to do. Let's do it quickly, okay? Aha, they asked us to find the average acceleration the body is experiencing during the impact. Now, average acceleration, the body, the particle is experiencing during the impact. So A, average, is question mark. Okay, so how did I solve it yesterday? Aha, I just needed to derive myself. I wanted to derive or remind myself what is expression for this thing. Okay, I'm gonna do it with you guys. Okay, so this is what I wrote yesterday in my notes. So I remember that F equals to ma. Of course, in our case, F is n. Yes, it's that normal force. Yes, and I know that I must integrate it from. Start listening to me. Thank you. Okay. From T0 to Tf dt, from T0 to Tf dt. Yeah, and I know that this is our impulse. Or IMP. Okay. So I know that our IMP is equal to integral from T0 to Tf ma dt. However, this guy can be a function of time. Yes, it does not. It can be. It can change. Yeah, like that, for example. Yeah. So so that integral. So the area below that curve can be actually replaced with area of such rectangle, where this is A average. So I think that that integral can be actually is actually equal to m a avg times delta t, where of course delta t is t final minus t0. Yeah, I can also put tf and t0 on the plot. This is tf. This is t0. Okay, find a average. A average is equal to IMP divided by m divided by delta t. So this is equal to exactly what we found in the previous part. So it will be 14.902. Mass was, I believe, 2.75, and Trevor said that impact lasts 10 times 10 to power of minus 3. Grab your calculators and obtain that this is equal to 5,419 meters per second square. You might think that this is the answer, and it is the answer, but they all ask us to express it in terms of G, okay? So actually A average is approximately 552.4 times G, and this is the answer. On the exam, I would accept 2, okay? But I'm not grading, yeah. Yeah. In my previous discussion, one gentleman asked me, how did I know that this is 552.4? I will tell you guys, okay? I just skipped one step, yeah? So A average is 5419 divided by 9.81, yes, times G. Yeah, if you plug this number in your calculator, you will obtain this one, okay? Questions? Finito. Yeah, we're done. That's all. Okay. So thank you for today and hope to see you next week. Bye.